Right now, the sun looks almost exactly the way it has looked throughout human history. A brilliant yellow star, 150 million kilometers away, rising every morning and disappearing every evening. But there's a clock hidden inside it, and that clock is already running. The terrifying part is that the sun probably won't need to explode, collide with Earth, or suddenly erupt to end our planet's habitability. It only needs to keep doing what it's doing now, burning. The sun is about 4.6 billion years old, and it's roughly halfway through the stage of its life, in which it fuses hydrogen in its core. As that process continues, the sun slowly becomes brighter. Eventually, that gradual increase in sunlight will push Earth beyond the conditions that allow our oceans, atmosphere, and complex life to survive. And here's the part most people get wrong. Earth's real deadline probably isn't 5 billion years from now. That's roughly when the sun will enter its spectacular red giant phase. Earth could become uninhabitable billions of years earlier. So what happens between today and the day the sun becomes a giant red star? And if humanity somehow survives that long, will there still be anyone here to watch it happen? Because the future of Earth isn't really a story about the sun dying. It's a story about the sun getting brighter. And that difference changes everything. The normal world. For billions of years, Earth and the sun have existed in an extraordinary balance. The sun provides the energy. Earth receives it. Our atmosphere redistributes some of that heat. Oceans store enormous amounts of energy. Clouds, ice, rocks, plants, and the carbon cycle all interact to regulate the planet. And at the center of the sun, something remarkable is happening. Its enormous gravity compresses the core to extreme temperatures and pressures. At roughly 15 million degrees Celsius, hydrogen nuclei can fuse together, ultimately producing helium and releasing energy. That energy eventually reaches the surface and radiates into space. We experience a tiny fraction of it as sunlight, and that sunlight powers almost everything familiar about Earth. Plants use it for photosynthesis. The climate system is driven largely by solar energy. The water cycle depends on it. Even much of the energy stored in fossil fuels ultimately traces back to ancient sunlight captured by organisms. It sounds stable, but stars aren't static. The sun is constantly changing. As hydrogen is converted into helium in its core, the composition of the core changes. The average molecular weight increases, the core gradually contracts, temperatures rise, and the rate of nuclear fusion increases. The result is a slow increase in the sun's luminosity. Astronomers have strong theoretical and observational reasons for knowing that sun-like stars become brighter as they age. Solar models indicate that the young sun was roughly 20 to 30% less luminous than it is today. Think about that. The sun that warmed the young Earth wasn't the same sun we see today. It was significantly dimmer. Yet ancient rocks show evidence that liquid water existed on Earth. So Earth has already survived one version of the sun's changing behavior. But eventually, the direction reverses. The sun keeps getting brighter, and that's where the stable picture begins to crack. The crack in the model. Here's the strange twist. When people imagine the end of Earth, they usually picture the sun becoming a gigantic red ball and physically swallowing the planet. That image is real, but it happens much later. The first major problem arrives quietly. More sunlight means more energy entering Earth's climate system. At first, the changes would be subtle, but over geological timescales, they become enormous. As the sun brightens, Earth's surface temperature rises. More water evaporates. More water vapor enters the atmosphere. And water vapor is itself a powerful greenhouse gas. That creates a feedback loop. A warmer planet produces more atmospheric water vapor, which traps more heat, which causes further warming. Eventually, Earth can approach conditions where losing water to space becomes increasingly important. NASA describes a future in which increasing solar energy drives water evaporation, while ultraviolet radiation breaks water molecules apart high in the atmosphere. Hydrogen, being extremely light, can then escape into space. The planet begins losing one of the ingredients that makes it habitable: water. And that's the shock. The sun doesn't have to physically touch Earth to destroy its habitability. It can do it from 150 million kilometers away. The timeline isn't exact to a single year, because Earth's future depends on complicated interactions between solar evolution, atmospheric chemistry, geology, oceans, and the biosphere. But NASA estimates that Earth could become uninhabitable for higher forms of life in a little over 1 billion years, as the aging sun grows brighter and the planet dries out. Other NASA material gives a broader estimate of roughly 1 to 2 billion years for major loss of habitability. So ask yourself, if civilization somehow survived for 1 billion years, would Earth still be recognizable? Probably not. Human reaction and early questions. Now imagine watching Earth from space hundreds of millions of years from now. There's still an ocean. There are still clouds. But the planet is gradually becoming warmer. The boundaries of comfortable environments are shifting. Some ecosystems disappear. Others migrate toward the poles, underground, or into increasingly specialized habitats. Eventually, complex ecosystems face an environment that becomes fundamentally different from the one that allowed them to flourish. And this is where the story becomes fascinating rather than simply frightening. Scientists aren't asking, will the sun suddenly destroy Earth? They're asking something much more precise. How does a living planet respond when its star slowly changes? Because Earth isn't just a rock sitting beneath a lamp. It's a dynamic system. The atmosphere changes. Continents move. Volcanoes release gases. Rocks absorb carbon dioxide. Oceans store heat. Life itself changes atmospheric chemistry. For billions of years, these processes have interacted with the sun. But eventually, the increasing solar output becomes a boundary that Earth's natural systems can no longer compensate for. And here's a question for you. If you knew humanity had 1 billion years to solve the problem, would you consider that an enormous amount of time or an unbelievably short deadline? For us, it sounds almost infinite. On the scale of civilization, it is enormous. On the scale of evolution, it's surprisingly short. Because Homo sapiens has existed for only a tiny fraction of Earth's history, the planet has already existed for about 4.5 billion years. Human civilization occupies only the last microscopic sliver of that timeline, and the sun has another surprise waiting. First attempt at explanation. For a long time, the dramatic ending people focused on was the red giant phase. And that phase really will be spectacular. In roughly 5 billion years, the sun will exhaust the hydrogen available for fusion in its core and begin major changes in its internal structure. It will eventually expand into a red giant. Mercury and Venus are expected to be engulfed. Earth's exact final fate is less certain. Why? Because the sun will also lose mass as it evolves. As the sun loses mass, its gravitational pull weakens slightly, and Earth's orbit can move outward. At the same time, the sun expands enormously and becomes vastly more luminous. So whether Earth is physically engulfed depends on the details of solar mass loss and Earth's orbital evolution. But there's an important point. It doesn't really matter. Because Earth would have been uninhabitable for complex life long before the red giant reaches its maximum size. By then, the oceans would already have disappeared. The atmosphere would have undergone profound changes. The surface would be nothing like the blue world we know today. NASA describes the sun's red giant phase as beginning roughly 5 billion years from now and lasting on the order of 1 billion years before the sun eventually becomes a white dwarf. And the sun will become dramatically brighter. NASA's current educational material notes that a red giant sun could be around 2,000 times brighter than today's sun. But here's where it gets really interesting. The red giant isn't simply the moment Earth dies. It's the final chapter of a process that began billions of years earlier. The real countdown started when the sun was born, and we're already living inside it. The escalation, new data. But then new data and better models changed the way scientists think about this story. The biggest revelation isn't that the sun will become a red giant. Astronomers have known that for generations. The deeper realization is that habitability is not the same thing as the physical existence of a planet. Earth could remain in orbit around the sun for billions of years after it has stopped being a comfortable home for life. That's a crucial distinction. A planet can survive. A planet can still have an atmosphere. It can still have oceans, or traces of them. It can still be visible from space. And yet it can be biologically hostile. Scientists therefore use concepts such as the habitable zone, the region around a star where conditions can potentially allow liquid water on a planet's surface. As stars evolve and their brightness changes, that zone moves. For the Sun, that habitable region slowly moves outward. Earth is effectively being left behind. Eventually, worlds that are currently frozen and far from the Sun could receive enough energy to become temporarily warmer. Research has examined how aging Sun-like stars can shift their habitable zones outward, potentially warming frozen worlds around outer planets or their moons. Imagine that. The same Sun that eventually makes Earth too hot could, much later, provide enough energy to warm worlds that are freezing today. So the future of the solar system isn't simply everything dies. It's a migration of habitability. One world loses its window, another may briefly gain one. And that changes the question. Instead of asking, how long will Earth survive? Maybe we should ask, how long can life follow the Sun? If this changes the way you think about Earth's future, hit like. It helps more people discover science stories like this. Because we're about to reach the point where the question stops being about planets and starts being about us. The real science. So what actually happens inside the Sun? The key is the core. Today, the Sun is converting hydrogen into helium through nuclear fusion. The core gradually becomes richer in helium. That changes its structure. As the helium concentration rises, the core contracts and heats up. The surrounding layers respond, and hydrogen fusion eventually occurs in a shell around the increasingly dense core. That produces more energy. The Sun expands. Its luminosity rises. And eventually, when core hydrogen fusion can no longer continue in the same way, the Sun enters the giant stages of stellar evolution. Later, the core becomes hot enough to fuse helium into heavier elements, primarily carbon and oxygen, but the Sun isn't massive enough to continue burning carbon in its core. So after its giant phases, the Sun sheds its outer layers. What remains is a dense stellar remnant, a white dwarf. NASA estimates that this final remnant will be roughly Earth-sized, despite retaining a substantial fraction of the Sun's mass. And this is one of the strangest facts about stellar evolution. The Sun will eventually become smaller than Earth, but it will be extraordinarily dense. The star that once dominated our entire solar system will end as a hot stellar core, gradually cooling over immense stretches of time. No explosion like a supernova. The Sun isn't massive enough for that. No black hole. It simply evolves. And that tells us something important about our own existence. Earth's habitability isn't guaranteed by the fact that the Sun is stable today. It exists because our planet happens to be inside a temporary window. That window has lasted billions of years, and it will eventually close. But the story isn't over, because the most interesting question isn't what happens to Earth. It's what happens to intelligence. Cosmic and planetary stakes. Picture Earth 4 billion years from now. If humanity were still here, it wouldn't simply be living in the same cities with more advanced technology. The planet itself would be different. The Sun would be brighter. The climate system would be radically altered. The ecosystems that evolved under today's conditions would be gone. Eventually, the surface could become increasingly hostile to complex life. And if humanity, or whatever descendants humanity becomes, wanted to remain in the solar system, it might need to move. Not necessarily to another star. At least not immediately. As the Sun evolves, the habitable zone moves outward. Worlds that are frozen today could receive much more energy. The outer solar system could therefore become an increasingly interesting place for future life. Jupiter and Saturn have moons with enormous quantities of ice and, in some cases, subsurface oceans that are already of intense interest to planetary scientists. But we shouldn't confuse possibility with certainty. A future habitable world would require much more than simply warming it. It would need the right chemistry, atmospheric conditions, stable environments, and enough time for life to survive or emerge. And there's another possibility. Humanity could eventually leave the solar system altogether. NASA has already framed this possibility as a serious long-term question. If intelligent life survives for billions of years, migration to another planetary system could become the ultimate solution to the Sun's evolution. But that assumes something enormous. that humanity, or its descendants, actually survives long enough to attempt it. Wars, resource shortages, asteroid impacts, technological risks, ecological collapse, unknown threats we haven't even imagined. The sun may give Earth roughly another billion years of habitability, but that doesn't mean civilization gets a billion years automatically. The clock we're most familiar with isn't necessarily the most dangerous one. And that may be the biggest twist in this entire story. If this changed the way you see the sun, hit like. Drop your biggest question about humanity's future in the comments. And subscribe for more real science, space, and cosmic mysteries.